Okay, so welcome everybody to the online series of talks on tunneling in QFT. Today we have a special guest from IJS, and it's Gianluca Lagnese, who will give us the 20-second talk in this series. And he will talk about a topic that is more, say, condensed matter oriented, perhaps. And it's going to be false vacuum decay in quantum spin chains and quantum simulators. Let me remind you that all of these talks are going to be uploaded on YouTube, and you can find them on Indico together with the slides. And also that the next talk is going to be in April by Kartik Rajiv, and you can also check out the one after that. It's already listed on the Indico. Okay, with this said, I think I leave the floor now to Gianluca, and I'm excited to hear what you guys are working on.
Okay, hello. So yeah, I'm happy to have the opportunity to give this contribution to this series of talk, and well, I just hope that if not like on the short term, at least on the long term, this is going to be at least a tiny bit useful, for some of you. So yeah, the whole idea is that how do you scroll here with the mouse? Okay. Okay. Okay, so let's say I would like to start a bit from the motivation. Of course, there are many possible ones, but one of the things I would like to stress that somehow this language of the spin chain, we can say it's naturally close to the language of many quantum simulators. And the thing is that, let's say, since like this very remarkable advantage that essentially are described. Do you see the mouse? Okay, so right. They are described actually in this review from this technology of ultra cold atoms. Essentially, they are able to, differently from, let's say, standard condensed matter setups, essentially. In this case, they are able to synthetically engineer a certain system with certain Hamiltonian, tune the parameters of the Hamiltonian, and they also able to realize different geometry and dimensionality, and they're also able to implement essentially lattice models, okay? And this sounds a bit naive, but essentially in this most simple setup, the basic element is a qubit, which essentially it's atoms which have two levels, which are essentially um, coupled somehow. And these two different levels, they can be seen such like 0, 1, if you want, or ground state, excited state, but also they can also be mapped to a spin up or spin down. So in the course of this presentation, I will just take what for us is kind of, like the minimal model of the phenomenology that we are interested in, which is the transfer field quantum chain. Then I will describe a bit in parallel also because I think this clarify a bit a few things in the way we see this phenomenology on our side, also confinement and false token decay in these models. And then I will pick up a couple of experiments that I find interesting. And of course, I mean, this is not, it's not meant to let's cover broadly the experiment, let's say, point of view, but I think this clarify a bit how, theory and experiment can talk closely, let's say, in this specific framework and what is like the ability that experiments they have at the moment. So let's start from the model. Okay, historically, of course, I mean, many of you, of course, you know that what the easy model, and it's like essentially it was introduced to describe magnetic properties of the material, because essentially it's like the most simple model that provides, let's say, transition from magnetic paramagnetic. And the spin, I mean, essentially it's just a reminiscent of the exchange interaction, which is between the electrons at the microscopical level. But we basically forget about it. And essentially this model, okay, in the classical setup, you have this interaction where essentially you can have an energy scale, which is J, and then you have like the spin that are located in the nodes of the lattice. And you have in this classical regular lattice, you have basically just nearest neighbor interaction, but you can have more complicated version of the model, which are not actually interested in this talk. And of course, the model has a certain, let's say, order parameter, which is like the spontaneous magnetization, and there is a certain temperature where in 2D you have like a second order phase transition from ferromagnetic to paramagnetic, where the expectation value of the magnetization is expected to be zero. But then, okay, you start from classical Ising, but then we have this object which is like a quantum Ising chain. And the 2D Ising is equivalent to the 1 plus 1, let's say, quantum Ising model. And here essentially, okay, here essentially what happens is that your classical spin operator are substituted by pole operators. And the transfer field is essentially what is driving the quantum fluctuations. So essentially here the transfer field, if we are at zero temperature, it's taking, and this is actually well explained in the book by Sachdev. Essentially, the transfer field is like driving the quantum fluctuations, and it's playing the role of the temperature in the classical Ising. Now, the I messed up. Okay, now we want to understand what are the main features of the models that are interesting for us. Okay, I will use this description, okay, of like a fully polarized state, okay? If like the transfer field is like smaller than one, the model is in the ordered phase, and you have two ground state which are fully polarized in the degenerate, okay? Of course, the degenerate is true in the thermodynamic limit. But then in the course of the, let's say, my presentation, what I use is this effective description, which is very intuitive, which is actually justified in the limit of very small transfer field, okay, which you can basically think of just this classical uh, combination where the system has this to say so the system is very polarized, okay, and the fundamental excitation are this domain wall excitation, which are actually interpolating between the two phases, okay? And what you can see here, essentially, you can effectively imagine that this is, let's say, an energy or a gap term, okay, the mass of this domain wall, which is associated to the existence of this domain wall. And here the transfer field gives the dynamics, essentially. So less is the field that makes these things hopping like over the lattice. But of course, this is more general because in 1 plus 1D, let's say there is this tool which is like a free fermion mapping, which essentially allows you to again to obtain some exact solution for the Ising model. And this picture is still qualitatively good. The difference is that the domain wall is not interpolating by two domains of which are fully polarized, but they are like they have some let's say finite value of the actually it's again the order parameter, which is the ground state magnetization. And what is important here is that this mass essentially it's like this mass and these two quantities are not perturbative in HX. So we're not adding correction with respect to the first picture. This is like exact like this. But it's so useful to think in the first like description because at the end of the story, it's good to qualitatively describe what we observe. Okay, now the second ingredient that we need is this longitudinal field, and this longitudinal field is very important because it's the one that breaks this degeneracy and gives you a finite density of energy difference between the two vacua. And this is the source of all the phenomenology that I'm going to describe. And yeah, of course, here, but you're all familiar with that probably. essentially the metastable minimum we call false vacuum, and the stable minimum you call it true vacuum. And yeah, now I will start from let's say from this part where I describe the phenomenology that we observe in the real-time dynamic, and this part is mostly based on these two works. One is mine and collaborators, other is actually from my ex-advisor and other collaborators. And just like some background, so essentially this phenomenologies, the fact that the easy model with longitudinal field present these like confined modes was already observed in some kind of experiment in material. Actually, these material, they're not exactly described by the Ising model, but they are kind of similar, okay, in a sense. And they were doing some, let's say, scattering experiment that they were able to isolate these masses. But then there is like this very old paper, let's say, from McCoy and Wu, which they were the first, let's say, to study the green function and understand that in the green function, actually, these like coupled, these like massive modes were emerging when in presence in of the longitudinal field and at temperature, which was less of the critical temperature. This was for classical Ising field theory, Ising model. But then, okay, the main difference here, as I already said, is that we want to address this from a point of view of the out of equilibrium dynamics. And this essentially, there are like these three concepts of Hegel that I want you to bear in mind, which are important from this point of view, which essentially we're working in these like isolated setups, okay? So, and there are no thermal fluctuation. The reason for this is like connected again with these like things that I said at the beginning, that thanks to the essentially experimental advantages and let's say discoveries and developments, uh, people have been able actually to simulate this system, closed system with a nice level of accuracy. And this stimulated the theoretical, let's say, development and vice versa, because then, okay, the system became even better and they be able to actually tabletop, let's simulate the dynamics that is described in the theory. And here I just like give you a couple of, let's say, good review for this kind of field that is rotates around the real time of equilibrium dynamics of these closed many body systems. The second one is especially, let's say, focused on the concept of quantum integrability. Okay, so since we are talking about non-equilibrium dynamics, essentially the main tool, which is like theoretical, but then became also experimental for this scope, is this quench protocol. What I'm describing here is the global quench. And it was essentially it's made of these three main steps. Usually you take something which some state, which is the ground state of a certain Hamiltonian, which is a function of a set of parameters. For our sake, let's say it's like a transfer field and a longitudinal field, I anticipate, but of course it's a general set of parameters. And then you pick up the state, but then at one point you suddenly change the parameters and you evolve the system with Newton time evolution, but with a new Hamiltonian. For what follows, what we have in mind is that these Hamiltonians are local. So basically, they are the sum of local terms, which means that they have a finite support with respect to the size of the whole system. Okay, this is very important because this is very important. Also, is also connected to the concept of this quasi-particle picture. Essentially, after the quench, for this kind of system, you can always often essentially imagine that you are producing locally, and because of locality, you know, this phenomenon, this is happening only at the local level. Otherwise, it wouldn't hold. If your initial state has a certain, let's say, correlation length, which is small, let's say all the particles that are produced within this correlation length, they start to spread across the system, and they essentially carry quantum correlation, okay? And there is this concept which is called the Lie-Robinson bound, which is again due to the locality of the Hamiltonian, for which essentially you will find the connected correlators only where you are inside this light cone, okay, which is somehow described from the maximal possible velocity of these particles when they propagate. And this is another review essentially because where this concept is fundamental because it's like fundamental uh, around this problem of relaxation and thermalization in this closed quantum system. But okay, this is like a side comment. Now, what is important is that from the point of view of this phenomenology that we're describing, now I'm starting with confinement. Essentially, what happens is that usually the easy model without the longitudinal field, and this is like exactly computed, essentially this local observable will basically just relax exponentially. But then what happens, and then you can basically observe it, we are performing a quench, these are the quench parameters, and we're performing a quench, but we are not quenching outside the ferromagnetic phase, so we are in the order phase, but we switch on the longitudinal field, and what happens is that the local observable is developing like stable oscillations, okay? And these are, in this work, they were basically comparing different numerical techniques and this like the presence of this oscillation is quite let's say evident and stable. But essentially, yeah, in this paper is actually where this like behavior was computed exactly with this like exponential decay that we would observe in the quench without the longitudinal field. But now what's happening is that in this quench phenomenology, the idea is the following, okay? You're starting with this like your initial state, but it's this state that was the ground state of the first Hamiltonian is not anymore the ground state of the new Hamiltonian. So essentially you can expand it in the basis of the new Hamiltonian, and you will see that it's coupled to the mode of the new Hamiltonian. But now a local observable, essentially it's sensitive to this like to these modes because you can basically just write explicitly the expression and you will see that they're sensitive to the modes. And even more, essentially, we can actually study this real-time evolution in Fourier space, and you will see that you will extract this mode, and this mode are actually we call M because they are actually connected to the masses of these like confined modes that they appear when the longitudinal field is different from zero. Okay. And we can basically borrow the terminology from high energy and call them mesons. Okay, essentially they are couple of excitation, but instead of propagating linearly, like I showed you before, after the quench, because of the longitudinal field, and this basically can be understood again with this like a picture, a very simplistic picture. These like bubbles that they explain, they pay the price for having like frustrated domain in between, and this prevent them essentially to propagate, and they start to develop this stable oscillation, and the frequency of this oscillation is actually the masses of the connected to these masses. And again, this is like the king mass, domain wall mass that I described to you at the beginning, and this is the difference of the energy density between the two vacua. Okay. And the thing is that these masses, they can be actually well described by two-body model, where basically you account for an effective Hamiltonian where you have like the dispersion relation of one particle, the dispersion relation of the other particle, plus this like a long-range interaction. Now, another very sharp effect it can be seen actually from the propagation of the correlators, and actually from the connected correlators. And essentially, while you have this light cone propagation when the longitudinal field is switched off, but then they start to restrict essentially this propagation propagation begins to be suppressed, and you start to see this oscillation when you turn on the longitudinal field. Okay, and actually very interesting. You can also see that like if you amplify the signal you can see that you also have the secondary domain wall which that are propagating because okay the most probable effect from after the quench is that you don't produce like four particles, okay, locally, but you produce, let's say, a couple of particles, and they are confined. But then, of course, there is also a signal that is due to a couple of mesons that they are propagating. But since they are heavier than the elementary excitations, they propagate essentially with a speed which is smaller than the usual speed of the bare excitations. And this is like detectable if you amplify the signal. And the other thing that you can observe essentially is that if you are outside this ferromagnetic phase, so the transfer field is bigger than one, you basically don't see anything, even if you switch on your longitudinal field. And these are just a couple of experiments just to show you that this is also already tested interestingly in some experiment, this suppression of the dynamics after the quench. One is actually developed from this EBN quantum computer from superconducting qubits, where they observed the suppression of the propagation of the light cone, similar with this trapped ion setup, where they see the suppression of the light cone, and actually they study also the behavior after the quench of the local observables. Now we can go to let's say, the main topic, which is the false vacuum decay. And essentially, what we are trying to describe, okay, we move our attention, of course, before we were studying, if you want, these modes that are on the true vacuum. Now I want to understand whether we want to prepare the system on the false vacuum and see what happens, okay? Of course, we are interested in the decay by quantum fluctuation, as I said, not by thermal. And this is principle, of course, it's detectable in the probability to stay in the false vacuum during the dynamics. And the decay rate is essentially that, like in the long time limit, um, we will see that the probability of the false value to the system to stay in this metastable configuration is decaying exponentially. But now we're lagging for this picture, which, as I said, works essentially in the small transfer field limit, which is like very intuitive. And but this clarify from our point of view how the thing is going. Okay, you're somewhere close to the false vacuum, and then you start to flip something. Okay, some spin. But this, of course, you will pay a price for this because you have to create, with respect to the false vacuum, you have to create two domain walls, so two particles. But the thing is that if the particles they start to be further apart, you start to gain some energy because of the domain wall. Sorry, for the domain which is like actually the true vacuum, which is enclosed by these two domain walls. And if you go further, you get to the point where you may actually compensate with this true vacuum, which is in the bubble, the energy price that you pay to create the two particles, okay? But the thing is that this process, okay, in this limit, this process can be, let's say, understood in the following way. So essentially, in order to nucleate this critical bubble, you need to move you need to do how many moves. This number of moves is actually given by this ratio. So this means that essentially to connect this initial configuration with this critical configuration, you need to do an exponentially large number of moves. And somehow this is like a kind of an intuitive explanation of why we get this dependence of 1 over the longitudinal field, which is the field that breaks the degeneracy. But then this was generalized by our Rydberg in his work, and essentially this was generalized for outside this limit where we are in a small transfer field, and was generalized in a way that this essentially holds if the, let's say, energy difference between the vacua is still like relatively small with respect to the energy gap. But this is going to give us essentially to us our theoretical prediction. Now I go back to the quench protocol because this is actually crucial um, for our numerics. Essentially, we prepare the system in the ground state of the Miltonian, so, where the two fields are switched to zero. So this is like fully polarized state. But then what we do, we perform some imaginary time evolution because we want to switch on the transfer field, but we don't want to essentially have effect of the transfer field in the quench after we propagate the system. So to obtain this, essentially we use imaginary time evolution to relax as much as possible close to the real ground state for this like hx, which is not anymore zero. So the state is not anymore the fully polarized state, okay? And then only after that, we will change the value of the longitudinal field. In this way, this configuration, which is was close, say, to the true vacuum, now becomes the metastable vacuum by changing the sign of the longitudinal field from minus hx to a hz. And from here, we perform the quench. One remark about the dynamics, essentially, intuitively what happens is that the dynamics goes along three stages, okay? You have like some short time dynamics, which is governed by off resonance state. Then you have some, let's say, low density of production of resonant bubbles, which happens essentially at the time scale, which is given by the decay rate. But then after a while, this bubble will start to interact and you will have a secondary process. Okay, well, once you have that, you enter in a completely different phase. And essentially, the difficulty to isolate this tunneling is to find, let's say, the good parameters for which you have a good separation of the time scale in order to isolate the dynamics. But essentially, somehow, it seems like we were able to find this like window, and this it's like evident in these two observable. I think actually it's better if we focus on the second one, okay, in this rescale monetization. This rescaling is just because, okay, in this way, essentially you have a function which in the true vacuum is zero and in the false vacuum is one. And then by fitting these lines in this like region where essentially they were kind of evolving because this is like an exponential, you can see essentially this exponential scale. Essentially, by doing this exponential filtering, we extrapolated the decay rate. And then, okay, we double this decay rate like as in principle as dependent also of the observable. And then we studied how the decay rate by performing different, let's say, fits that depends on the 1 over the longitudinal field. And actually, what happens is that we saw that somehow the perfactor is not always right, okay, in the expression, or at least we are not able to fine tune, let's say, the protocol to perfectly achieve with the theory. But the extrapolated dependence in the exponential is actually very good, okay, for both observables, I would say that is convincingly good, okay. And this is more or less, let's say, the main result that we were able to isolate. So now we begin the second part, which is focused on the experiments. And I selected these two experiments, which interestingly, basically, they are based somehow in they are two different devices, okay? But they're based on the similar technology in the sense that they use this like rubidium 87 atoms, just they are employed in a different way, okay? So one experiment is this like technology which is called the Rydberg atom. And essentially they individually trap this atom in optical tweezers. And then they have some lasers, which are actually these two lasers, these like red, these are the wavelength lasers, that they use to connect the ground state to a very excited state, which is this Rydberg state, okay? In the other case, instead, they use an optical lattice, and the dynamic is described by Bose-Hubbard model, essentially. where these atoms, so they are cold, they're very cold, so they go to microkelvin, and essentially they're just able to hop or to interact on the same side if you're on the same side, or to hop from one side of another. Okay, and they are trapped on the lattice. Of course, the idea is that like the rubidium has different transitions in the energy level, and some transition are exploited for the trapping, and others are exploited for the interaction in different way. Okay. Now we start from these Rydberg atoms. Actually, this picture is obtained by the documentation of one of these devices, which is like Aquila is called. But this is just to, because I think it's nice to have an idea of the complexity, because actually they have 6 lasers, because they have lasers for cooling the atoms, lasers to manipulate the atoms, lasers to manipulate interactions, lasers to read what's happening, essentially, to perform the measurement, and so on and so forth. So it's quite interesting. And this is an example because they have these optical tweezers. Essentially, they're kind of able to move the atoms like singularly from one place to another. So now we go back a bit more in detail on how essentially they work. As I said, essentially, you have two main energy levels which are used. One is very high of energy, which is this so-called Rydberg state, and the other is like the ground state. They are coupled by two lasers, okay, and this gives rise to these Rabi oscillations. So this parameter is related to this Rabi frequency, is related to this Rabi oscillation. And then you have something which is called detuning, which is essentially the difference in frequency between the transition and the frequency of the lasers. They are not exactly the same. And this gives you the ability to tune these other parameters. Actually, for these setups that we are interested in, they have one global detuning, but they also, let's say, to perform this site-wise, so for atoms, they are able to implement this also to this staggered structure, which we call a local detuning. This is a bit more technical, but like the philosophy is the same, essentially. And then what's very important is that the Rydberg atoms, since like you have this very high excited state, they have this van der Waals interaction that behave they decay with the space very quickly. Okay, and what happens is that if the atoms are close enough, the potential becomes very big, and essentially this will suppress configuration where two close atoms are excited. But for instance, maybe this falls, let's say with space, this interaction falls quick enough that the next nearest, let's say, atom will not feel this interaction and can be excited. So this will give you this like a staggered structure, up, down, let's say 0, 1, 0, 1, up, down, up, down. Okay. But now we understand, now we'll connect with the Ising model, because this Hamiltonian with the component that I showed you, which is like this Rabi frequencies with coupling which is coupling the different level, this detuning and this like van der Waals interaction by selecting, as I said, they can essentially in their experiment they tune the position such that you can neglect all the others interaction, and they keep only the nearest neighbor interaction. And they tune the potential, sorry, they tune this global detuning such that it's equal the potential. You can essentially map to the Ising model. Actually, you can map to the antiferromagnetic Ising model. The phenomenology is essentially the same as I described you before, just that now the order parameter is like antiferromagnetic magnetization, because now the order is antiferromagnetic, because this component here will essentially select disaligned couples. And then again, you have your Z2 symmetry and your two ordered states with this identification, essentially. So the longitudinal field will be identified with this like um, local detuning, and the transfer field with this Rabi frequency. And now again, we have our picture that I showed before. So this is completely analogous to what I showed before. As I said, this is like two ordered ground states. They are nil and anti-nil, but okay, when you introduce the local detuning, you break the symmetry, you have this energy difference between the two vacua, and then again you have the same phenomenology. Essentially, you create your excitation, you change in a small domain the order, you pay the energy price, which is given by the energy scale because you're creating these two domain walls, but then if the wall is like big enough, you can eventually compensate. And this basically connects easily with the phenomenology that I described you before with the easy model. And now what's interesting to me is that essentially they were able to replicate the essentially the same protocol. They just define this quantity similarly, but as I said, now there is this antiferromagnetic order. Otherwise, everything is similar. And they study this quench protocol in this like logarithmic scale. They perform the fit, they extract the decay rate. What's interesting is that they essentially here they are doing the quench for a certain value of the Rabi frequency, which is like the transfer field, but they are starting from the nil state, so essentially exactly from this full polarized state. And essentially, they see that with the experiment, they start to deviate, and the behavior of the decay rate essentially is not like ideal. But what's interesting is that they actually somehow perform the same protocol that I described to you before to essentially clean out the effect of the transfer field. Okay, so they perform, of course, okay, in the numerics, we perform imaginary time evolution. In the experiment, they perform this adiabatic ramping. So essentially, they just very slowly change this parameter such that you don't excite anything, but you move from ground state to ground state. And they essentially show that by starting from this, because the new state is the fully polarized, this other state is this like state which is prepared with this protocol. And they somehow I would say convincingly able to find, let's say, this region where the decay rate is actually evolving, is actually behaving exponentially with the inverse of the local detuning, which is, as I said, the parameter that breaks the symmetry. And actually, they say that this gray line, it's not a fit. Actually, it's like without any fitting, this is like the theoretical prediction. So the one from Rutgevich, essentially. Adapted, of course, with the parameters that are involved here, but they don't perform any fitting, essentially. So it's like, I would say it's like convincingly nice. In the second one, sorry, in the second one, this is a fitting, okay, but because now they're just showing that even if they tune a bit away from these like requirements that for the mapping, it's like this, like the tuning that like the global tuning is actually equal to the potential V. They are the same. This is required for the mapping to easing. They're just like highlighting that even if the model is a bit more complex, you're move away from this mapping, you're still able to maybe isolate a region where they see this like let's say sufficiently clean behavior of the decay rate with inverse of the local detuning. Ah, yeah, sorry. This is I mentioned, but okay. Just wanted to highlight that this basically, again, this like a theoretical prediction without fitting. Now we move to the second setup. Again, this is based on this other work, and again, I mean, it's like
Sorry to interrupt. Can I ask a question about the previous setup?
yes, sure.
Yeah, I was wondering how big is the spin chain in their experimental setup, and
Yes,
how big is the critical bubble?
they okay. Essentially, they commented this. Okay, anyway, these are the sizes, 16 and 24. And they essentially in general, but they also provide here I'm not showing everything, of course. They provide also some material in the supplemental material where they show that what they observe is not dependent in of the system size, and they make sure that the critical bubble essentially it's sufficiently small that they don't see any effect, like I see, because of the fact that the system is finite.
Okay.
So yeah, because otherwise, I mean, this I didn't mention. In our numerics, they were using some numeric techniques that they are actually very efficient for the spin chain, where they explicitly exploit translational invariance. And so up to, say, some numerical precision, which is, however, under control, we know that you are simulating some system which is actually in the thermodynamic limit. Of course, in the experiment, you cannot do this, so you will always have some finite size. But they comment that what you observe, it's like robust will change by changing the system size.
And do they comment on the end state at the end of the evolution? Because you have a finite system, you nucleate this bubble,
Yeah.
and eventually, as it grows, it will become sensitive to the size of the system. So you will settle to some sort of.
Yeah, I see what you mean. I mean, I didn't see any detailed, let's say, I think they addressed this, but they didn't, let's say, tackle exactly what you're asking, I think. Okay.
Okay, thank you.
Okay. So, okay, so this setup is a bit different, okay, because this connects to this like, okay, this somehow deviates a bit from, in the sense that this is an attempt to realize lattice gauge theory on a quantum simulator, okay? And the idea is that they're essentially starting point from this Hamiltonian, which is the Schwinger model on a lattice. So essentially 1+1 quantum electrodynamics on the lattice in the Kogut-Sutskin, I don't know if I pronounce it right, formulation. Where the components are essentially, you have that on the lattice side, you have the matter field. The links are this parallel transporter. And you have this background field, which somehow is a topological term. And of course, okay, the mass term of the excitation, okay? The thing is that, okay, forgive me if I don't give you many details on this, but the thing is quite long. I hope, like, of course I can say a bit more, but essentially I'm skipping some step, but at the end of the story, in these quantum devices, what you do is that if you study the canonical commutation of your, let's say, link operator, you will see that they behave in the electric field. You will see that actually they behave like angular momentum operator. So they identify them with some angular momentum operator, and the electric field is identified with essentially the SZ, while these like lattice links, so these like parallel transporter, they're just changing the electric flux. So this is like, for instance, S plus, the other dagger is S minus, or vice versa, okay? And now what happens is that because of this energy term, you will see that the spectrum is organized in discrete value of the angular momentum of the big S, so essentially. And this gives you a natural way to truncate the space, because the problem is that, of course, on a quantum device, you cannot really, like rely some continuum link variable, okay? So you need to truncate. And the most, let's say, simple truncation that you can do is that you can select S1 half, okay? So that you have only two values of the electric field. And you go to this like a quantum model formulation, which is essentially exactly the same, but in this case you select the Spearman half systems, variables. This model obey anyway the Gauss law, which is written here. It's a bit strange. Okay, this is like extra components just to the fact that there is this staggered formulation. Otherwise, this is just like the flux. This is a Gauss law operator, which is also the generator actually of the gauge transformation. But this is actually crucial to the mapping that you're using. But before the mapping, okay, I will just like mention something about the phase diagram of the model. So, because maybe this would highlight why this phenomenology is actually similar to the easy model phenomenology. So so you have this like background field, which is depends on this angle. And there is some specific value for this angle, which is basically this is like this is actually just theta minus pi. And you have a certain value of m where again you are in an ordered phase. You have your Z2 symmetry, you have your ordered phase, and you have like two degenerate ground states. But then this background field will break the degeneracy. And the certain value of the mass, will have some second order phase transition. While if you tune away from this mass, but you are in this phase with this ordered phase, this like longitudinal background field will basically drive you to this first order phase transition. So this connects to this like idea of breaking the degeneracy between two vacua. And now the mapping is based, let's say, as I said, on this like Gauss constraint. This is a bit like more, this slide is a bit filled up, but essentially on the top you have your atoms hopping on the lattice. On the bottom here you have your quantum link model formulation, where I'm just introducing this notation. Essentially, arrow right is like a spin up, arrow left is spin down, and then you have this means essentially +1/2 or -1/2 for the electric field, okay? And then because of the Gauss constraint, you have only these two possible configuration allowed when you create some particle or antiparticle. So essentially the dynamic of the particle is completely fixed with the dynamics of the field. So if you want, you can write this equation integrating away using the Gauss law to integrate away one of the two. But essentially what happens is that this tunneling term is actually which is described from the Bose-Hubbard by the hopping of excitation, will essentially flip you the field and create you particle-antiparticle. These terms give you the mass that you pray to create particle and antiparticle. And this one, as I said, is the one that breaks essentially the degeneracy of the two vacua. The parameters, this is like the, let's say, dictionary parameters from Bose-Hubbard and quantum Lie model. But if you want the identification, as I said, with the quantum Lie model and easy model that I described you before, is essentially that this is the longitudinal field and this one is playing the role of the transfer field. Which brings us again, like in the similar picture that I showed before. So you eventually can prepare your state by selecting the proper sign of the longitudinal field. You can make sure that your ordered configuration is somehow the one that is like higher in energy, the one where the electric field is completely flipped, okay, to the other side. So this is like up, 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 up. This is my down, 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 if you want. And when eventually what you expect with the quench, that you will like nucleate a particle and antiparticle, which means that you are nucleating a domain which is like favored in energy. And eventually, the bigger the domain is, the more you are like closer to the critical bubble. So this somehow connects with the same phenomenology as before. Just let's say maybe the results here are less like I would say to some extent they're less clear, but I'm going to describe what's happening. Okay, so essentially here they are studying the particle production after the quench and the overlap with the initial state, because I mean the good thing is actually that they are able also to compute the state overlap in the dynamics, which is quite remarkable because I mean they did mention this, but essentially in their dynamics they have to perform because every time you measure, of course, you collapse. So at every time you measure, you have to do a different run to go, like you have to do several runs to have all the measures at several times, because every time you have to basically reset everything and start from the beginning. Anyway, what is nice, I think, is that they are able anyway to study how this external field essentially it's like increasing the production of particles, and this is actually this having like an effect on both the particle production and also the vacuum amplitude. Or actually here they have like the probability of to stay in the initial state. These like solid lines are actually simulations and simulation like numerical simulation just to test whether the algorithm is like so whether the experiment is like doing well. Let's say the problem, so the main missing, let's say, point here, because for technical reason they couldn't do yet, okay? It's like they cannot do this adiabatic preparation to relax, okay? So the problem is that, as you can see, they are not able to isolate only the effect of the longitudinal field somehow, but they still have some dynamics, which is due to the fact that they are quenching from the mass to infinity, or if you want, let's say, to this like fully polarized state to a different value of the mass, or vice versa, to, let's say, a finite value of your transfer field in this case. But nonetheless, I think it's like from the experimental point of view, it's like a very nice result that they somehow can actually simulate like this instability, the effect of this like external field in the production of pair production, which, as I said, from the point of view of the field, is actually bubble dynamics. It's just that in this case, like as I said, they cannot do this, let's say, state preparation protocol, and they're actually quite far away, let's say, from this limit where the bubbles are large. Okay, so this is like a kind of a very small bubbles that are created and then annihilated back. Okay, somehow.
Sergio,
Yeah.
can you remind us what is this color code here?
Oh yeah, sorry, the color code is just if this I just forget to mention. So these are like these are different value actually at this value of the longitudinal field. So of this sorry for the missing. Okay, this H, this field H, sorry. This field H, these are different value of the field H. And actually it's like a 0, 0.7, 1.4. So these are actually big numbers at one point. So it's kind of, like the critical bubble, if you want, is very small somehow. Just quickly, like to mention, of course, this was this experiment, I think, was addressed by Ian Moss somehow in the where the difference is that this is not like a lattice, this is a fluid. But I just want to mention that there are, like different experiments going on. These are very nice results from a couple of years ago. And this is also like a nice recent result where they, it's like another setup, it's a quantum annealer, where they studied somehow this like nuclear, it's still like somehow focused on bubble dynamics. They kind of tune the longitudinal field to nucleate, let's say, to observe nucleation of bubbles of exactly a certain decided established size, which is dependent of the longitudinal field. And this is like from one of our collaborators here at the institute. So this brings me to the conclusion. I'm done. Just to resume, somehow my main message is that I want to show you, let's say, how these spin chains, from our point of view, they can be seen some kind of toy models of this like non-perturbative phenomena. And how, let's say, for us, it was a bit natural, I would say, to address this phenomenology from the real-time dynamics of Lobach observable. And then I just selected a couple of experiments that I thought were interesting to somehow show how the interplay somehow between theory and experiment in this like setup. So at least how for this kind of models, let's say experimental realization are quite close somehow to the theory language. Of course, I mean, in the future, I mean, of course, but this is already, there are few works that are going in this direction. Like the problem is going in either direction and somehow, let's say, understanding how to extrapolate, even though that you're simulating somehow on a discrete device, how to perform a good scaling of the parameters to actually extrapolate quantities to the field theory. And somehow this is like I think this is the main let's say step in the future that we are aiming for, I would say. So with this, I thank you for the attention.
Thank you, Gianluca. Yep. Very good.
Are they dead?
I'm not sure. Doesn't seem that way. Good. So if you have questions, just raise your hand and unmute yourself, and we can go ahead with the Q&A session. Yeah. Sorry. Yeah, Alex, maybe you want to go first?
Yeah, hi. Thank you, Gianluca, for the very nice talk. I was curious with these spin chain models. So I guess that at if I were to imagine taking the kind of continuum limit of this and writing it down as a field theory, I guess each spin has more than just this magnetization degree of freedom, right? Because it has some kind of phase degree of freedom of how you rotate it around the X and Y axes. So and I guess this must play some role because you have this the transverse field that somehow controls the quantum fluctuation. So I was curious if you could just talk a bit about what that extra degree of freedom looks like and how it participates
Uh-huh.
in this dynamics.
Okay, what I can tell you, okay, so I mean, of course, you can play with other models, okay, but in this case, okay, if you are in 1 plus 1 dimension, okay, and you want to tune to the field theory,
Hmm.
you actually don't need somehow extra degrees of freedom. What you need to do is actually to perform, and this was actually, I think, was by Zamologic of there are known the relation. Essentially, you need to study how the system, how you scale the parameter to the phase transition. So essentially, maybe I can go, yeah, okay, oh yeah.
We can then go back.
Okay, I mean, I can just say by words, and then you can ask if it's not clear. So essentially, I think this happens in the sense of mm, scaling limit, which means that you reintroduce essentially the lattice spacing, which is actually encoding the energy scale, okay? Because the
Hmm.
energy scale is 1 over the lattice spaces, essentially. What you want to do is to send the lattice spacing to 0, but at the same time, you want to send the parameters to the close to the critical point, okay? Because when you go to close to the critical point, there it's where essentially the field theory is well defined because it's like the correlation length, it's exploding. Somehow when you introduce back um, the physical quantities like the lattice spacing, essentially the correlation length is like like it has like a dependence of the lattice spacing. When
Hmm.
you do this, essentially, uh, what happens is that you know that at the critical point, you're going close to the easing field theory because if you are in 1 plus 1D and you have a Z2 symmetry, then you know that your field theory is so the universality class around the second order from phase transition described by this easing field theory. But then you can extrapolate. I mean, in other work, we try to, let's say, address some quantity in this setup. You can essentially cleanly extrapolate your quantities to the one described by the field theory. If you really follow this prescription, that, as I said, essentially you tune the lattice spacing to 0, but at the same time, you will essentially send which actually is like the transfer field, HX, you will send it to 1, which is the critical point. If you do this carefully, then you have like a well-defined, let's say, continuum limit. Because otherwise, if you don't have continuum limit, you lose the observable, you lose the masses, for instance. But
Hmm.
if you do this, you will preserve the mass scale, which is like this.
Okay.
Yeah, I can go back.
I think you can.
Yeah, sorry.
Sorry, I clicked on the text on the
No,
chat.
it's okay. Blah, 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 blah. Yeah. Somehow this, okay. So essentially, you want to preserve this mass scale, okay, when you introduce your lattice spacing. So essentially, here in the place of 2, you will have like 1 over a, essentially.
Hmm.
And then when you send a to 0, you want to send also hx close to 1, such that this quantity is fixed, okay? And this is like a well-defined, let's say, scaling limit. Yeah. In this case, you don't need extra degrees of freedom. Then, of course, there are different models, and other models, they have a different way to perform this, essentially, and that's it, you know. From
But
the
so in this scaling limit you've described, what does the field theory look like? So do the X and Y, values of the spin play
it's
any
like
role?
not really. It's like essentially the field theory is described by free fermion. So you have like free Majorana fermions. Whether I don't know whether this tells you anything. I mean, in the end, they are like uh, somehow they're not like Dirac fermions. They are Majorana, so they're kind of real. So in a sense, they are like a half of a Dirac fermion. Okay, and it's like they're free. Okay, and then the field theory, the longitudinal field, it's like again, is the field that is breaking you somehow. The role is the same of the parameters, and you have you usually say that we have on top of this like free fermion, you have two perturbations. One perturbation is like this energy perturbation, which is the one that gives you the mass, and it's like a field which is Z2 invariant, and the other field is the field that breaks the Z2 invariance, which is like the longitudinal field essentially. And there is like the way the reason why in this way the limit is well described is that you can actually establish a one-to-one mapping between the field on the lattice and this field in the continuum. But
Hmm.
the conformal field theory, it's this like free Majorana fermions. It's like this easing field theory.
Okay.
If you change the dimensionality, then it's different. If I'm not wrong, for instance, in 2 plus 1 is 5 to the, actually you get to 5 to the fourth. So your conformal fixed point is 5 to the fourth, for instance.
Okay. Thank you.
Two more questions. First is Ian. Maybe you have to
Hi,
unmute.
I got a little bit. Yeah. Thanks. That was a very interesting talk indeed. I sort of a general question about both the numerical simulations and the experiments.
Yeah,
It'd be
sure.
quite nice if you could see the bubbles. Have you any thoughts? For example, whether we could see how big they are when they nucleate. Have you any ideas whether you might see this either in the numerical simulations or in the experiments?
But they are doing, I mean, I'm aware of a couple of both simulations and experiments. There are simulations where, for instance, they are trying to study bubble collision, for instance. Because in principle, it's technical, but numerically, you can prepare, for instance, two bubbles and then send one of two over each other, and then they're just like crash, and then you can study the collision. And I think they are doing also, there are also some experiment on that. Okay, one experiment is this one that I mentioned. Um, But I think okay, so I think this experiment is very interesting. It's just maybe from the sake for the sake of field theory, it's a bit far away of the field theory limit somehow. Okay, but in this experiment, at least this it's nice that they show somehow that how you can basically what you do is that they change the longitudinal field and they select exactly what's the critical size of the bubble, and they observe, like that in the experiment they essentially measure and they nucleate exactly the critical pipe bubble of that size somehow.
So, which experiment are you talking about?
One is this
On the right.
this one this one on the right. Okay. Otherwise, I just don't remember. But eventually, I can. Uh, maybe. What if I Google it? Can I Google maybe?
Well, there's no need. I don't think there's no need to look it up.
Because it's like
I just
this.
wonder, it's just that I mean the one evidence for the nucleation theory is the rates, but another one is the critical size bubbles.
Yeah, I
And
think.
just seeing how big they are. That, by the way, in these the quantum annealer case, I had the impression that they weren't in the proper bubble nucleation regime. I thought they didn't have like a highly non-perturbative bubble production. It looked more perturbative to me. Is that?
Yeah, yeah, it's true. They're kind of close to this, like, I mean, if you want, in the language of the presentation, they're close to this, like a small transfer field limit. Yeah, I agree.
Yeah.
Um, I have a couple of papers that are nice in mind.
Oh, just put them in the chat or something. I
Maybe
don't
I can put it in the
know.
chat. Yeah, or maybe I don't know. Maybe it's easier. I mean, if I'm allowed, maybe I can send you an email if you want. Maybe it's easier.
Yeah, I'm just Ian Dutmos.
Yeah, because I'm not on my laptop. Sorry. It's like, yeah.
Yeah, that is very interesting.
Yeah, yeah. I mean, I'd be glad to help. Yeah.
Okay, so we had another question from Sergey, actually. So go ahead.
Thank you, Gianluca, for interesting talk. My question is about the decay rate and the analytical predictions of decay rate. You know that there are, in fact, two different predictions. Why one was made by Voloshin in 1998.
Yeah.
It was relates to the field theory limit, and another one was mine, a completely different calculation, but it turns out that difference between these results is just a numerical factor, pi squared divided by 9. So it's
Yeah, yeah, I
equal to
know
1.
very well this. Yeah, this issue.
My question, is it possible to see this difference somehow in either in numerics or in experiment? It's still not possible. It's difficult.
Yeah, I mean, okay, I might be wrong, but like at the moment, I have the feeling that like I think we need to improve. I mean, a little bit more the ability of the experiment. Like to address this more like fine-tuned detail. I would say probably there will be this opportunity, but at the moment, I think there are some limitations on the, let's say, of these setups. Of course, they are remarkably good now, but I think there are still a couple of problems, like technical problems to address, in order to go for these like more fine-tuned issues. Although I have to say that, I mean, I was actually, just a second. I actually don't know whether they hit I mean, this is actually interesting to me because I don't know whether they hit a sweet spot or what, but somehow they claim that here this like gray line, okay, is actually exactly the theoretical prediction, okay? And they refer, let's say, to the theoretical prediction that we had for these observables, let's say, on our paper. But I mean, at the end of the story, it's your theoretical. So it's like this is like it's inheriting the expression from your theoretical prediction. So maybe we are close enough, I have to say. The problem is that, I mean, now I don't understand whether, like this is like, because they don't, I think we need to do this a bit more precisely in order really to rule out, whether the right expression is yours or Woloshing ones, And I think it's that we're not at that level of precision at the moment. And I think also numerically it's hard, I would say. Although I wanted to try a bit more.
Okay, thank you very much.
You're welcome.
I just want just one comment about this. So the common belief was that the Voloshin's result was exact and mine was approximate due to some approximation I have used. And I was bothered by this equation for many years, but now I believe I have some progress. So I improved my old calculation and
nice.
obtained the result, the new result for this prefactor, and it contains some infinite number of series which converges. And if I take just the first term in this series, I reproduced my old result, but if I sum all the series, I recover the velocity. So it's likely
This is
that
very interesting.
velocity result is
Yeah.
exact.
But you know what? These guys here actually they did some let's say calculation for phi to the fourth actually. So for the
Right.
field theory. And they are actually also claiming that there are correction on top for the phi to the fourth, there are correction on top of this like Voloshin's prediction. So
Yeah.
so actually, I mean, I think we are on the same
Directions.
yeah, the same direction. So actually Voloshin is not the definitive prediction. Somehow it was some kind of I don't know if we have to say that first order, let's say, prediction, even
Of course, there are corrections, but the leading term, it's likely that the leading term is exact, leading asymptotic.
Okay, interesting.
Yeah, very interesting indeed.
Yeah.
Okay.
Okay, thank you.
Thank you for all the questions and for your interest. So this was a very nice discussion. I really enjoyed your talk, Gianluca.
Thanks.
Thank you for your contribution. So, anyways, I think we'll wrap it up here, and we'll see you in April. So, in about a month. Okay. Thank you.